I'm Ahana, a postdoctoral researcher from the Department of Chemical Engineering, IIT Madras. Here I'm going to discuss my work on polymer crystallization at high directional velocities. Directional crystallization is a process where a sample is subjected to a moving temperature source that induces melting followed by solidification of the material. The picture here represents the experimental setup where we have this white region, which is the sample. It is being pulled above this heated metallic rod that act as a source for this material. So the temperature inside the material is shown here. So we have a peak temperature, that is the point where this material comes in contact with this heated metallic rod. Therefore, that region of polymer gets melted. And on the two sides of this, we have the semi-crystalline zone. This directional crystallization results in spherulites that are elongated in the flow direction, as shown in this picture. These spherulites are different from what we get in usual isothermal crystallization. Directional crystallization process improves the mechanical properties of polymer material. So the objective here is to model the directional crystallization of polymer materials induced by a moving heat sink. And we also want to find the temperature and associated crystallinity profiles. The schematic here represents the system that we have considered. We have this one-dimensional domain, which is this black line, which is the polymer at its melting point and its molten state. So at time t equal to 0, we introduce this moving heat sink at the left side boundary, which is moving with the velocity v. So at any time t, it will be located at vt, which is represented by this red line. And the interface between the solid and the melt, which is this blue line, will be located at x0 of t. At any point in this material, the temporal change in the temperature is given by this 1D unsteady heat equation, which has contributions from three terms. First term, which corresponds to the heat conduction from the surrounding, and the second term that is coming from the latent heat that is released during the crystallization process. And this last term represents the presence of a heat sink or source in the system. Here phi is the crystallinity, and the growth kinetics of crystallinity is given by this equation here. It's a simplified version of the Abrami model. By non-dimensionalizing these two equations, we get these two boxed equations. These are coupled equations and needs to be solved simultaneously. For that, we use method of lines and RK4 method, and we perform 1D simulation. From the simulation, we get the temperature and crystallinity profiles. Here I've shown these profiles at three different velocities of sink. So in all these plots, the dashed curves are the temperature profiles and solid ones are the crystallinity profiles. And the star represents the location of the sink. So at low sink velocity, we see that to the left of the sink, we have a constant temperature, which is equal to the temperature of the sink. With increase in the sink velocity, we see a rise in the temperature to the left of the sink. And this increases with increase in the sink velocity. So there is a change in the polymer crystallization with change in the sink velocity. So we can divide the polymer crystallization into different regions on the basis of sink velocity. So here we can see this separation of regions, and this is done based on the ratio of W by delta and velocity of sink, where W is the interface thickness and delta is the distance between the sink and the interface. And here region 1 represents the region where W is much smaller than delta, and region 3 is where W is much larger than delta, and region 2 is an intermediate region where W and delta are comparable. And here region 1 is the region where we have a boundary layer separation. And in the second plot, we see this temperature on the left boundary, which is plotted as a function of velocity. So in region 1 and 2, we have this constant temperature, which is equal to the sink temperature. And in region 3, that is at high sink velocity, we see an increase in this left side temperature, and it reaches to the melting point of the material. We similarly plotted phi max, which is the maximum crystallinity that the system can attain. And here we see that in region 1 and 2, it remains constant, and it is in region 3, it starts decreasing. So region 1 and 2 corresponds to a complete crystallization and region 3 represents an incomplete crystallization. We have also calculated the heat balance or heat duty in the entire domain. For that, we have divided the domain into 3 zones. Zone 1, which is the region to the left of the sink, and zone 2 is between sink and interface, and zone 3 is from interface to the right side boundary. So in all these 3 zones, we have integrated this heat balance equation and calculated each of these terms. In this, the first term represents the conduction, that is the heat that is being conducted away by the sink, and the second term that represents the latent heat, that is the heat that is being released during the crystallization, and the third term, which represents the convection term, which is coming because the polymer material is moving from right to left in the moving frame of reference. So all these terms contributions are plotted in these 3 figures corresponding to these 3 different zones. And in zone 1, we see that there is no heat transfer happening in region 1 and 2, that is at low sink velocities, whereas we see a significant amount of heat transfer in region 3. And this is the reason for this rise in temperature that we observed in the previous plots in zone 1, that is to the left of the sink. And in zone 2, we see a heat transfer in all these 3 regions, but we see an increase in this heat transfer with increase in the sink velocity. And clearly there is a distinction between region 3 and region 2. And in zone 3, there is only negligible heat transfer that is happening, and that too in region 3, and it is not much of importance. So from all these analysis, based on the velocity of the sink, we see that the directional polymer crystallization can be divided into different regions. Region 1 and 2 corresponds to a complete crystallization, and region 3 corresponds to an incomplete crystallization. And numerical results in region 3 shows a rise in the temperature to the left of the sink, and this is happening because the sink is moving so fast that the crystalline energy profiles are not fully developed. And we have also calculated the heat duty and identified the contributions of different modes of heat transfer in these 3 zones. So thank you so much. For more details, you can contact me through my mail ID.